Greetings everyone. Today we're going to be covering Lecture 22 in Kinematics and Dynamics of Machines. This lecture covers a portion of Chapter 6, specifically Section 6.9, which discusses interference, which we'll get to that concept in a moment, 6.10, gear tooth forces, and then we'll also have a few words about Sections 6.11 and 6.12 so that we can talk about failures in gear materials. As always, I urge you to read the relevant sections in the book. I'm covering the high points, but you should be looking for additional information. Alright, interference. We've discussed before that involute gears in general, have a rolling type of contact. This in effect is, if you're looking at a plane, a point contact. When you're looking at three-dimensional gears, you have a line contact. That involute profile exists between the base circle and the addendum. If you recall how we created the base circle and saw how the involute curve was generated from it, should be pretty evident that that's where the involute exists. Any areas of the tooth that are outside of that section, so any areas outside of the line from the base circle up to the addendum, will not have an involute profile. Sometimes, depending upon the gears, you may have contact occurring in that zone, and if you do, it's called interference. There's a nice picture showing the interference. It's shown in Figure 2, the undercut. This is from your textbook, and you can see the black portion here. This is a portion that is cut out or damaged by the interference from one gear tooth to the other, which is what occurs when you have that contact outside of the involute. When you manufacture a gear via hobbing, which we took a look at in a previous video, any gear tooth contact outside of the involute area would have been cut out of the tooth. So technically it doesn't have interference, but you do get this undercut area, which, as you can imagine, greatly weakens the gear tooth in bending. Now, it's fairly easy to calculate the maximum addendum circle radius to avoid undercutting. So we're going to take a look at sample problem 6.10 on page 440. Let's now take the opportunity to illustrate the concept of interference by taking a look at sample problem 6.10. This is on page 440 in your book, and it reads as follows. Two standard, so full depth spur gears, 20-degree gears have a module of 8 millimeters. The larger gear has 30 teeth, while the pinion has 15. Will the gear interfere with the pinion? So this is a fairly straightforward problem, and it's worth illustrating a couple of things here. First off, we see that these gears have a module, therefore they are metric or SI gears. That allows us to very easily calculate their pitch diameter, and that's usually a good first step whenever you're working with any gear problem. As I'm sure you recall, the module is defined as the diameter of the pitch circle divided by the number of gear teeth. We also remember the convention that gear 1 is the smaller of the gears. Often gear 1 is called the pinion. Gear 2, the larger of the gears, is usually just called the gear. So going back to this, we can calculate the pitch diameter of gear 1. It's going to be equal to the module multiplied by the number of gear teeth, which in this case will be 8 multiplied by 15, or 120 millimeters. For gear 2, same calculation. So very, very straightforward. It's also very easy to remember the center distance equation. If you recall, C is equal to 1/2 multiplied by the diameter of the pinion plus the diameter of the gear, which in this case is equal to 180 millimeters. Now if we flip back to the notes, do that momentarily, what we're trying to do is calculate the maximum addendum circle radius that the gear can have in order to avoid undercutting. So that's this formula. Let's go ahead and reproduce that just so we don't forget it. It says that the maximum addendum radius for gear 2 is equal to the square root of the base circle radius for gear 2 squared plus center distance squared multiplied by the sine of the pressure angle. So there's one other thing here that we need to calculate, and that's the base circle radius. Remember, the base circle radius is the radius that's defined when you first manufacture the gear. It's the radius of the circle off which the involute curve is defined. The equation for the base circle radius is equal to the pitch radius multiplied by the cosine of the pressure angle. So that tells me, implies, that the pitch circle radius for gear 2 is equal to the pitch radius, which is 1/2 of the pitch diameter, so 120 multiplied by the cosine of 20 degrees. So 120 times the cosine of 20 degrees gives me a maximum pitch circle radius of 112.76 millimeters. Or excuse me, it gives me the base circle radius. Getting a little bit ahead of myself. So that's my base circle radius. I can now calculate my maximum pitch circle radius. I'll go back to my calculator here. I'm going to take and square base circle radius. Maybe I'll go ahead and just cut that down to a reasonable number of significant digits. And I need to add that to 180 squared, that's my center distance, times the sine of 20 degrees squared, and then that whole thing needs to be the square root. So this tells me, therefore, that RA2 is equal to 128.47 millimeters. That is the maximum addendum radius that this gear can have and still not interfere with the pinion. Now, as you recall, in table 6.1, we found that the addendum for a metric gear A is equal to the module, which in this case is 8 millimeters. So that says that the actual, I'll go ahead and note this as the max. So the actual addendum radius for gear 2 is going to be equal to the pitch radius, which is 240 divided by 2, or 120, plus the module, which is 8, or 128 millimeters. So this tells us that the gear radius is actually, the addendum radius is smaller than the maximum addendum radius that we can allow. It's 128 millimeters, and we could go up to 128.47 millimeters. So in this case, the gear does not interfere with the pinion. As an exercise, I'm going to suggest that you go back and calculate the maximum addendum radius for gear 1. What you'll find is that it is significantly larger than the actual radius in this case. And that's a general thing. Whenever you're looking for interference, check the maximum addendum radius of the gear versus its actual addendum radius. Any interference will show up there first. So that concludes sample problem 610. Let's get back to the lecture. As we said, the larger gear in any gear pair is the one that will show interference when you calculate those maximum addendum radii first. So always go ahead and check the larger gear. We can get rid of or eliminate the interference by using more teeth, but then that requires that the pitch diameter for our gears increases to transmit the same amount of power. We'll take a look at how you calculate the power and the forces a little bit later in this lecture. You can also change the pressure angle to reduce the size of the base circle. You may want to sketch this on your own, what the pressure angle is in relationship to a pair of gears, in order to convince yourself that this is the case. This leads to fewer teeth and smaller gears, which may have an issue or another set of issues that you don't want. You can calculate the minimum pressure angle that's necessary to eliminate interference by knowing the center distance, the pitch radius, and the maximum, or excuse me, the addendum radius. Finally, for interference, there's a limiting condition on the number of gear teeth that you can use to avoid it. It can be calculated by knowing the radii, the pitch radii, addendums, and the center distances, as well as the pressure angle. If we substitute in some numbers, we can build a general inequality. If we are looking at a rack, meaning something like a rack and pinion, where the large gear becomes just a straight line of teeth, we can calculate that inequality a little bit differently. So these are things just to keep in the back of your mind, maybe play around with the equations a little bit. Remember that you have that nice calculator for a reason. It's lots of fun to play with. And also finally, you can create non-standard gears if you have an interference problem by shaving the tips off, in effect reducing the addendum radius of your given gear. However, I don't recommend doing this. It creates a non-standard situation, and one of the great strengths of using spur gears is you can buy standard gears, and standard gears are very well understood. So by shaving the gears, you're increasing your costs and maybe making it a little bit more difficult to do maintenance later on. All right, let's talk about gear tooth forces. This is a very important topic. I'm going to perhaps spend a little bit more time on it than I would normally in a video, because we would be spending more time in the lecture, because I would see whether or not people are understanding the concept. So I'm going to take this fairly slowly, and we will stop for a sample problem at some point in the lecture portion. Now, as we said, gears are a very old but very effective technology for transmitting power. They're one of the most efficient and most effective means that we have within our technology. Gear forces are transmitted through the teeth, so we've got a very effective and very useful means for transporting power. We get a fixed ratio of speeds between the gears, and we get a fixed amount of force on the gears. That gear force is applied, very difficult to see in this picture, you can blow it up or take a look in your book, but it's applied along this pressure line. Remember, that's where the pressure angle comes from. This means that the force on the gear tooth is normal to the surface of the gear tooth and passes through the pitch point. This force resolves down to two forces that we're going to care about in turn spur gears. There's a tangential force, Ft, and a radial force, Fr. The tangential force is equal to the normal force multiplied by the cosine of the pressure angle. The radial force is equal to the normal force multiplied by the sine of the pressure angle, or the tangential force multiplied by the tangent of the pressure angle. These forces do two things. The radial force first always acts to move the gears out of contact. So in the case of these two gears shown at the picture in the top, that radial force is trying to push them apart. It's trying to increase the center distance between the gears. Always. When you create a bearing arrangement or shafts to hold gears, the force that those shafts and bearings are reacting is this radial force. Sometimes you'll see the radial force called a gear separating force. Sometimes you'll see it called a bearing force. Again, because gears have been around for a long time, it's collected a number of names. The tangential force, though, this is the force that we actually want. This is the force that is generating a torque around the gear. That torque is equal to the tangential force multiplied by the pitch radius of the gear. Remember that the tangential force passes through the pitch point. It is perpendicular to the center lines of the gears, and therefore we can calculate the torque as the tangential force multiplied by the pitch radius. This is what we want to use gears for, both for that fixed speed ratio that's defined by the number of teeth, or by the velocity ratio, which can be defined by the number of teeth or the sizes, and we want it for transmission of torque. Why do we want to transmit torque? Because gears are used to transmit power. For mechanical uses, and this is a very, very important equation to remember, mechanical power is equal to the torque multiplied by the speed. If you take a look at the units here, it should be very evident that if your torque is in Newton meters and your speed is in radians per second, you will get units that are equivalent to watts. So mechanical power can be described in terms of watts. This is an important insight, guys, and it's worth spending just a moment on. Whenever you're looking at any engineering problem, it's well worth your time to try and do some kind of a power balance or energy balance. If you're doing this, you can equate, for instance, the amount of electrical power being put into a system in watts with the amount of mechanical power. So generators can work this way, electric motors can work this way. You can see what your electrical power in as compared to your mechanical power out is, and therefore get an efficiency number. There are a couple of legacy calculations included on this sheet that give you just unit conversions basically for horsepower and kilowatts. In general, when you're doing this kind of calculation, I do suggest that if you have English units, it's worthwhile translating them into SI units, performing your calculations in SI units so that you have nice, consistent, easy to understand units, and then translating back to imperial. Therefore, one of the worthwhile imperial unit conversions to always remember is that 1 horsepower is equal to 746 watts. Next sections are 6.11 and 6.12. I should point out now that after looking at the forces and the powers and the torques on gears, normally at this point we would work through sample problem 615, but that's an important enough problem that I want to do it in person in class rather than only do it here on the video. So we'll move directly into the next sections. Gear tooth failure, there's a lot to be said about this. Not very much, frankly, in your book. Oftentimes you will find gear teeth failing due to fatigue. I have worked in the past with the Cornell Fracture Group, which has some very interesting videos up online. If you download the notes and click on the link shown, you'll see some fairly interesting things. So fatigue is one way that gears fail. Generally, this is coming from the bending stress on the tooth, and as we said, we just talked about the torque going through the gear, which is the product of the tangential force and the radius. That tangential force is what causes the bending stress on the tooth. When we look at gear tooth stresses, this isn't really mentioned in our book, but it's worth saying a minute about. More often than not nowadays, we'll see gear tooth stresses determined by FEAs, and that's generally the best way to do it. If you do need to get a rough calculation, just to see if you're in the ballpark though, you can use the tooth form factor. This is a fairly old calculation. It's based on something called the Lewis form factor, tables for which are very readily available online. You'll note that this is in PSI only, so you're going to need to translate your forces from newtons into pounds force. It's equal to the tangential force, which we just talked about, multiplied by the diametral pitch. So that should be ringing the alarm bells at English units only for this. Divided by the face width, which is the width of the gear. You'll note that this is the first time we have mentioned the face width or the width of the gear at all. It really doesn't come into very much in the discussion of basic spur gear calculations. We will see it though when we look at helical gears. Anyways, divided by the face width multiplied by the Lewis form factor, which is a number that you pick off a table. Your book also has virtually nothing to say about gear materials. Suffice it to say that now you can get many gear materials. Commonly available would be steel in various grades, cast iron, many different forms of plastic, brass. Sometimes you'll even see some oddball materials. Whatever material your gear is made out of, you want to pay attention to the contact stress. So in other words, what kind of stress you're getting on the surface of the tooth where you're actually applying the load. The bulk stress within the material. Lubrication conditions. Any kind of surface modifiers like coatings or surface treatments. Things like shot peening, ion nitride, and case hardening, other hardening techniques. All of these go into the thought process that makes up selecting gear materials. Again, very broad topic, so not mentioned in your book at all. I have given you a couple of interesting references to look at. We've discussed a couple of times that gears are a fairly old technology, and as such we see them in a lot of different gizmos. We see them used quite often because they're an efficient technology. One of the more interesting things that's come up in current time are microelectromechanical systems, or MEMS systems. If you have a cell phone, chances are the accelerometer on there that lets it change the screen orientation when you move it around is a MEMS device. You can see lots more about MEMS technology, which can include gears like are shown on the screen. I've seen devices that include miniature turbines to generate power. See lots more about them just by doing a very simple search for MEMS technology. So again, if you want to be the life of the party, that can be a good thing to do. Well, that concludes Lecture 22. As I said, we will do sample problem 615 next time we are together face to face. In the meantime, I will look forward to seeing you at the next lecture.